Hi, algebra students. Today we're going to talk about 611, which is the line of best fit. So let's first read this problem, 6-1. The championship is on the line between Tinker Toy Tech and City College. Robert plans to attend Tinker Toy Tech next fall and desperately wants to see the game, which has been sold out for weeks. Surveying the exterior of the stadium, Robbie has discovered a small drainage pipe that has a direct view of the field. The stadium is being prepared for the big game, and a maintenance van is currently blocking the view from the pipe, but the van will be removed prior to the game. The south end of the field is 50 yards from the end of the pipe, and the field runs from north to south. The total length of the playing field, including the end zones, is 120 yards. The pipe will be at the center of the south end of the field. The width of the field is 53.3 yards, about 160 feet. Investigate how much of the field Robbie will be able to see when he looks through the pipe at game time. So here is the data that we are going to use right here. And we're going to first start by plotting the data. Before we do that, I do have a picture of the situation here, which is kind of small. So we're going to look at this bigger version. So here's the bigger version. Here's the pipe. So imagine he is standing like right up against the pipe, and then he has this kind of field of vision. So here's the 50 yards right to the field, and then 10 yards here, and then this is 100 yards, and then 10 yards here. So the idea is the further back he stands from the pipe, it's going to change how much of the field he can view. So you can see here by this data, right? So when he's 144 inches from the wall, he can see 20.7 inches of the field, and so on. So this is the table, and I've already gone ahead and plotted the data. So if you have not, you should pause the video right now, and you should plot the data. Okay, mine I know is a little bit messy, but you can see my scale. You can see, here's the width, here's the distance, and you kind of are going to have to eyeball where some of those points are just because it's not an exact grid. So if you haven't graphed it, go ahead and take a minute to graph it. Okay, so now part C asks you to draw a line of best fit and determine the equation. So a line of best fit is the line that kind of goes through the middle of your data, follows the general trend of the data. So this seems to be increasing from left to right. If possible, this is pretty strong linear data. If possible, you want to maybe try to have as many points above as below. But if you have one point that's really skewed, then you don't necessarily have to use that reasoning. All right, so I'm going to, I'm going to try to get a line here as best I can, kind of through the middle. I don't like it. I'm going to undo this one. Sorry. So let's see. Let's try here. Maybe I want this angle to be a little bit. There we go. That one looks a little bit better. All right. So here is my line of best fit. And so now what it's asking me to do here is to draw a line of best fit and determine the equation. So we want to think back to, chapter 2 when we were writing equations, and we want to figure out our equation for our line of best fit. So we're going to pick 2 points on our line. And when we pick our 2 points, they do not necessarily have to be data points. In fact, in most cases, they will not be data points. So I want 2 points on my line. Let's do this actually. I want 2 points that are on my line. And if I can, I want it like this one here seems like a lattice point right there. You kind of see that point there. That's at 100, 15. So I think I'm going to use that one. And let me see if I have another one that looks like it's on a lattice point, like really close, like maybe this one right here. What does that look like? That looks like maybe 30 and 6. So I just want to be really clear that the points you pick, if you have a data point that falls on your line, great. If you don't, then like in this case here, then I am going to use the ones that do fall on the line. So it seems like I said, see here, what was it, 30 and 6? and then the other one was 100, and then 15. Okay, so a lot of times people are like, oh, I'm just going to pick any 2 points on my line. Well, sometimes you might have lines that are kind of not really points that really aren't close to your line. You don't want to use those. Okay, so to find our slope, what we would do is we would kind of make a table and we would put our 2 points on it. So we'd have the 30 and the 6 and the 100 and the 15. And we say, okay, well, from here to here, I'm going up, 9? And then from here to here, I'm going up 70. And so my slope is change in y over change in x, which would be 9 over 70. So that's what I'm going to use for my slope, which comes out to be about 0.13. So we're going to use decimals here. I know back in chapter 3, often we wouldn't use decimals because we really want to clearly see the rise and the run. With data, especially since there are decimals in the data, it is okay. Okay, so then I want to find the y-intercept, which is kind of a pain to like make a table and sort of back it up with this sort of slope. So we're going to use that strategy where I pick either one of these points here, and I'm going to put the 30 as my x. I'm going to put that in place of my x, and the 6 is my y. I'm going to put that in place of my y, and my slope is 0.13, so I'm going to put that in place of my slope, and then I'm going to go ahead and I'm going to solve for my b value. This is a b. It looks like a 6. It's supposed to be a b. So if I do 0.13 times 30, so I get 6 equals 3.9 plus b, and then if I subtract the 3.9 to both sides, I get that b equals negative 2.1. Okay, so that is my y-intercept. So then my equation is y equals 0.13x minus 2.1. Now, if you had chosen 2 different points, your line, your equation might be or your equation might be a little different, and your line might be a little different, depending on how you plotted your points, what scale you used, if you estimated a little bit differently. In fact, when I had done this earlier, I had picked 2 different points than these, and I had a different answer. It's close, though. I had the same slope. My y-intercept ended up a little differently, maybe because I tilted my line a little differently, so that is okay. It should be close. Now, next it asks you to describe the association. So you might be thinking, what does that even mean? Way back, there was a math note, and the math note talked about if you look at data, like how to describe the association. So if it seems like the points are tending to fall on a line, you would say it has linear association. If it seems like the points are increasing, you would say positive because it would have a positive slope. If it seemed like they were decreasing, you would say negative association. And then you talked about like strong or weak or moderate. This looks like a pretty strong and then positive linear association. So we are going to be referring to that idea quite a bit, this chapter, this idea of association. So I'm going to actually just type this because my handwriting will be really not great. Okay, so this has strong, positive, linear association. Right, so it seems like it's like a line with a positive slope. It's linear and it's pretty close to the line. The data falls pretty close to the line. That's where that strong is coming from. All right, so then it asks you to interpret the slope in the context. So that means, what does this 0.13 mean in the context of the situation? So remember, slope is the change in y over the change in x. And in this case, our y was the width of the field, and the x was the distance from the wall. So this is the width of the field, and this is the distance from the wall. And these were both in inches. So if our slope was 0.13, and we can think of it as being over 1, that means as the distance from for every inch we increase in the distance from the wall, the width of the field will increase by 0.13 inches. Okay, so we can write it a couple different ways, but we could say the width of the field increases by 0.13 inches for every increase of 1 inch in the distance from the wall. So see how I really related it to what the slope was. So this is my change in y over my change in x, and I'm kind of putting that into the context. All right, then the interpretation of the y-intercept in context. So our y-intercept was this negative 0.21. So my y-intercept is negative 2.1 inches. And remember, the y value again was the width of the field. And the y-intercept is when x is 0. So when the distance, in this place, x is the distance from the wall. So when the distance from the wall is 0 inches, the width of the field is negative 2.1 inches. Now, in this case, that does not really make sense in this context, right? To have and obviously when you look through the hole, you can see something, but that has to do with our line maybe being a little bit off from our data. So in some cases, these will make sense in context, but in this one, it just doesn't make sense. In fact, when I had calculated it with a different 2 points, I got a y-intercept of 1.67, and that would make a little bit more sense in context. But it will depend. And as you notice, everybody could have a slightly different line. And so we want to kind of streamline that. And that'll be a goal in this chapter. Is to find out a way we could all get the same line with the same amount of accuracy. All right, so then 6.2 asks us to predict how wide in yards Robbie's field view will be at the end, at each end of the field. So at the north end and at the south end. So if we go back to this picture that we had here in the north, he's standing here at the south end. So the distance to the field is right now 50 yards. But when we talk about at the north end, it'll be the 50 plus this 10 plus this 100 plus this 10, which will actually be 170 yards. So when we're talking about the south end of the field, we're talking about being 50 yards away. And when we're talking about the north end, we're talking about being 170 yards away. Now, the information, though, that we're given, our formula, if you remember, was that we would be in inches. So what I first need to do is I need to convert this 50 yards into inches. So you might remember that if I know that 1 yard is 3 feet, and if I know that 1 foot is 12 inches, then how many inches are in a yard would be 12 times 3. So then that means that 1 yard is 36 inches. So if I want to convert 50 yards into inches, then what I would do is I would kind of go 1 yard goes into, so 36 inches. So basically 50 times 36, which is 1,800 inches. Okay, for this 170 yards, I want to go from yards to inches, and I know 1 yard again is 36 inches. So that's 6,120 inches. So now what I'm going to do is I'm going to use that formula that we came up with on the previous page. So if I want to predict how much he'll be able to see, so here I would do y equals 0.13 times 1,800 minus 2.1. And then here I would do 0.13 times 6,120 minus 2.1. So let's go ahead and figure that out. Okay, so this comes out to be 231.9 inches, but the question asked, we want it in yards. So now I have to take the inches back to yards. So then what I would do is I would now end up dividing by 36 to get 6.4 yards is how much you would be able to see of the field. Okay, so then for this other one, I'm going to multiply the 0.31 times the 6,120 and then subtract the 2.1 and I get 793.5 inches. But then again, I want that in yards. So I would divide by 36 and I would get 22.04 yards. Okay, so the idea in this chapter is going to be that we're looking at data and we're trying to come up with equations and then we're trying to notice different patterns about the data.